OCR A, A-level physics, and this is my first video on the magnetic fields topic. Magnetic fields number 1. So here's a bar magnet, which is an example of a permanent magnet, and it produces a magnetic field. We can't see magnetic fields, but we can see the effect, in this case, on little bits of iron filings. And you'll see that these little bits of iron are lining up with the magnetic field. Now, magnetic field lines, a bit like gravitational field lines, electric field lines, the arrows show the direction of the field. Now, what is the direction of the field? It's the direction of the force that would act on the north pole of another magnet. Which is basically from north to south, because it would be repelled by north, it would be attracted to south. But the arrows show the direction of the force that would act on a north pole. And with other field lines, the closer together the lines are, the stronger the field. So in this case, the field is strongest near the poles of the magnet. And this is an example of a non-uniform field. Now, Hans Christian Ørsted discovered that currents produce magnetic fields. So we have a long straight wire, and when there's a current flowing through that wire, these compass needles are deflected. Now, the shape of the field, how would you draw field lines for this? The field is circular, and it is clockwise in the direction of the current. Looking at the field lines, and it's pretty obvious really that the field gets weaker as you move away from the wire. Yes, so this is the field due to a long straight current carrying conductor, and the field is clockwise in the direction of the current. This is the field due to a solenoid. So we get our piece of wire and we wrap it round a toilet tube, and then we put a current through it. And what you'll notice is that we get a field which is very, very similar to a bar magnet. Inside the solenoid, the field is actually pretty uniform, but outside the solenoid, very, very similar to a bar magnet. This is the field due to a current carrying flat coil, a flat circular coil. And again, looking in the middle, the field is kind of looking uniformish in the middle. Very often in physics, in particle physics, we use these things called Helmholtz coils, which is a pair of coils which it goes around one of these vacuum tubes. But the idea is that in between the coils, there is an approximately uniform field. You should recognize these fields, by the way. It does mention them in the specification, so you should recognize these fields. Okay, magnetic flux, psi, magnetic flux. We imagine a substance flowing from north to south. So looking at the field lines in the arrows, imagine some stuff. The word flux means flowing. And we imagine stuff flowing through space from north to south. And the amount of flux is the symbol psi, and that's measured in Webers, which is WB. Now, the strength of the field is the amount of flux flowing through a certain area. If you imagine the field lines were closer together, there's more flux flowing through a certain area. And so we call that the flux density. I know that density is usually divided by volume, but in this case it's divided by area. So B equals psi over A. So that's Webers per meter squared. And magnetic field strength is flux density. So magnetic field strength is measured in Webers per meter squared, or Tesla. There's Wilhelm Weber, and then this guy on the bottom right, Nikola Tesla, one of the cleverest blokes who ever lived. And magnetic field strength, you can measure it in Webers per meter squared, or Tesla, or something else we'll see very shortly. B equals phi over A. Here's a little sum for you to do, pretty straightforward. And the answer is in 3, 2, 1. Okay, so phi equals BA, so 2 times 10 to the minus 6 Webers. As the field lines, remember the field lines spread out as you move away from the magnet, so the flux density is getting less, so the field strength is getting less. Okay, now something different. A current carrying conductor at right angles to a magnetic field experiences a force at right angles to the current and to the field. So this is force on a current, this is. So we have a current carrying conductor, a wire with a current flowing through it, and that's at right angles to a magnetic field. Yes, there's my magnetic field B, there's my current I, and we get a force which is at right angles to both of them. Yes, the direction of the force is reversed if we reverse the direction of the field or the current. And we find that the force is proportional to the strength of the field and the current and the length of the conductor in the field. So on this diagram, the length of the conductor in the field is from there to there. Yes, so the force is proportional to B and to I and to L. Now, why does it experience a force? You don't really need to know this, but it's basically the two magnetic fields interacting with each other. Yes, you've got the field due to the current. Remember, that's clockwise in the direction of the current. You've got the uniform field. When you add them both together, you get this weird diagram. Now, field lines are a bit like rubber bands, and they have a tendency to straighten. So you can see that there's lots and lots more field lines underneath the wire, and that's going to push it upwards. It's called the catapult effect. You don't really need to know this, but this is why a current experiences a force in a magnetic field. To find the direction of the force, something very useful, something you need to know, is Fleming's left-hand rule. So starting with the thumb, hold out your left hand, like on this diagram, starting with the thumb, force, field, current. Yes, starting with the thumb, force, field, current, or FBI. And that's quite easy to remember, isn't it? FBI. The definition of the Tesla. Now, we haven't defined the Tesla. Basically, the field is 1 Tesla if the force is 1 Newton per meter, so it's 1 meter, and the current is 1 amp. Yes, if a long straight conductor carrying a current of 1 amp experiences a force of 1 Newton per meter when at right angles to a magnetic field, then the strength of the field is 1 Tesla. So that is our definition of the Tesla. B equals F over IL. So a Tesla is a Newton per amp meter. Yes. Rearranging that equation, we get another very useful equation, F equals Bill. While I'm here, B is F over IL. That's magnetic field strength, newtons per amp meter. Remember that gravitational field strength was newtons per kilogram, wasn't it? Yes, and electric field strength is newtons per coulomb. Newtons per coulomb. Magnetic field strength, newtons per amp meter. Okay, so magnetic field strength can be measured in Tesla, and it can be measured in Webers per meter squared, and it can be measured in newtons per amp meter. They're all equivalent units. The Weber is actually defined in terms of the Tesla. This diagram should be pretty obvious. If the current is at right angles to the field, then F equals Bill. If the current is parallel to the field, then there isn't a force. And then at any other angle, F equals Bill sine theta, where theta is the angle between the current and the field. In all of these cases, if you do your Fleming's left-hand rule, then the currents will be, the force on the current will be into the screen. It will be going away from you into the screen. Now, this apparatus here, you should know this experiment. So, saying that, it may come up in the exam. Okay, yeah, I believe you should have done it as a PAG, yes. And this apparatus can be used to find the magnetic field strength between the poles of a magnet. So if you look, we have these magnets which are on top of these electronic scales. And what we do is when there's no current flowing, you zero the scales, so it reads 0. Then you turn on the current and you have it so that the wire is pushed upwards. And if the wire is pushed upwards by the field, then the magnets are pushed downwards. And from Newton's third law, the force will be the same. And so you take the reading off the balance, and that tells you the force, and then you know the current, and you know the length of the wire in the field, so you can work out the field strength. And having said all of that, there's a little sum for you to do. So get that done, and the answer is in 3, 2, 1. There you go, 94.2 millitesla. That's a cat, by the way. So here's a bit of a summary for you. Permanent magnets and currents and moving charges produce magnetic fields. I mean, a current is a moving charge. The direction of the field is the direction of the force on the North Pole. You need to recognize the field due to a long straight wire and a solenoid and a flat coil. Magnetic field strength is B, capital B, and it's measured in Tesla. And magnetic field strength is also flux density, so that's Webers per meter squared. So B equals phi over A, where phi is the flux in Webers. A current carrying wire experiences a force in a magnetic field. The direction can be found using Fleming's left-hand rule. Remember, FBI. And then the size of the force is from F is BIL sine theta. F is Bill. Yes, F is Bill sine theta.